Hello everyone, and welcome to the online biotransport class. It's Friday, March 13th, 2020, and as you all know, we're in the midst of the COVID-19 pandemic, and it certainly turned our world upside down. So, lots of changes going on out there with all the social distancing. We're seeing major sporting events canceled, other things like symphonies and Broadway shows and so on. So all of these things have been canceled as we all try to, kind of stay away from each other and stop the spread of this infection. So, with this little, I guess I thought with all this going on, we could probably turn this into a good teaching moment. So what I wanted to do in this special lecture, which you won't be tested on or anything, but I thought you might find this rather interesting. I thought in this special lecture that we'd look at the mathematics of epidemics and look at one of the popular epidemic models that are used out there with some variations, and we'll end up getting a set of differential equations that we can solve easily using Matlab to kind of take a look at how this epidemic's going to progress over the next 6 to 12 months. And it'll also give you a chance to see why the decision makers are making the decisions that you're seeing happening, like the closing of universities and schools and instruction going online and so on. And also you'll see that the mathematics of epidemics is very similar to what we're talking about in biotransport, same types of equations that we solve in pharmacokinetics, which is in another chapter of my book here, and also in biochemical engineering, the modeling of biochemical reactions and the design of bioreactors and so on. So there's a lot of nice things that we can learn by taking this epidemic and analyzing it mathematically, and hopefully when you get through the math you'll be a little more informed about the usefulness of mathematics in biology and bioengineering and so on. So let's get started, and I'll walk you through the math model and show you some results of the MATLAB simulations. Okay, so what we're going to talk about is a epidemic model for the COVID-19 virus. This is also called the SIR epidemic model, where the SIR stands for susceptibles, infected, and removals. This is based on a model developed by Kermack and McKendrick back in, I think it was around 1927, and it's been used ever since, and the model's been validated with actual data that's been collected over the years from real epidemics. And basically we denote three new variables, S, I, and R. They're going to be our dependent variables that we use to follow the course of the infection. And S stands for the susceptibles, and those are the folks that can actually get the infection. And then the variable I will be the infectives. Those are the people who actually have an infection at some particular time, and they're the ones that can pass it on to other people. And then the R will represent the removals, and these are the people that have had the infection and now are either immune to it, they're in isolation, or they passed away. And what we do is we assume that we have a fixed population, which we'll call N. So N is the fixed population. And since the population is fixed at any particular time, the sum of the susceptibles, the infected, and the removals all have to sum to give the size of the fixed population. There's also a next level of this particular model called the SEIR model, and they add a fourth variable, which they call E of t, which represents a population of folks that are in a latency period where they're not actually showing symptoms. We're not going to develop that type of a model here. We'll just stick to the SIR model. But I do have a paper that was just published in the very prestigious Lancet Medical Journal where they talk about the SEIR model. So what's going to happen then in this particular model is we basically think of the progress of the infection as happening just like a chemical reaction. So we can say that the number of susceptibles that become infected, that happens at a rate that we can give by beta, which is a rate constant, times the number of susceptibles and the number of infected. This is just a simple mass action type rate law that we see in all kinds of bioengineering and chemical engineering fields. And beta is what we call then the infection rate. So this is a constant that we'll have to determine from experimental data for the infection. And then the infecteds, they'll be infected for a period of time, and then they become what we call the removals. That'll be a separate population of people that have had the disease, and they're either now immune isolated or dead. And the reaction rate for going from infected to the removals is described also by a mass action type law. This case here, it's just a first order rate law where the removal rate's proportional to the number of infected, and the proportionality constant is given by gamma, and that's called the removal rate. And the removal rate's interesting because the reciprocal of that is a measure of the length of the infectious period of time. It's sort of a measure of how long you actually have the particular infections. So what's basically happening if we just take the circle here, let me show you the circle. You can see in the circle we have a population of S's and I's, and these folks are all freely mixing just like we do in the US. We can move around all over the country, and as the infectives move around, they're going to be transmitting the virus to the susceptibles. And then what's going to happen is we're going to be removing a population of people, and we'll put them over in the special box because they're the ones that have already had the infection, and they're not going to pass it on to anybody. So what this means then is with these rate laws that we just talked about, and if we remember accumulation equals in minus out plus generation minus consumption, we can write the first order differential equations as I show inside the box that describe the disease process. So the rate of change of the number of susceptibles would be given by this rate expression here, where that's equal to minus beta times S times I. And the rate of change of the number of infecteds would be beta Si minus gamma I, using these rate laws that we talked about. And then the rate of change of the removal population is just proportional to the number of infected. And I call these equations A through C. Now, in order to have an infection that propagates and grows, di dt, the derivative or the slope of the rate of change of the infecteds with time has to be greater than 0. So in order for this term to be positive, that means beta times Si minus gamma I has to be greater than 0. Or when you just rearrange that expression, that means that the number of susceptibles at any time has to be greater than the ratio of gamma and beta. And this ratio gamma beta, we also give the symbol rho. So at time equal to 0, at the beginning of the infection, if it's going to grow and become an epidemic, the number of susceptibles has to be greater than the ratio that we call rho. Now rho equal to gamma over beta is also called the relative removal rate, and that's the removal rate gamma relative to the infection rate beta. Sigma, which is also equal to 1 over rho, is called the infections contact rate. If we multiply the contact rate, the infections contact rate, by the initial population of susceptibles, then that gives us what's called the R0. A lot of times recently in the news I've heard people like Dr. Fauci talking about the R0, or what's also called the reproductive rate or the reproductive number, and we can see that that particular number, R0, is equal to beta times the initial number of susceptibles divided by gamma. And this represents the number of secondary infections produced by one primary infection. For an epidemic to grow, R0 has to be greater than 1, and the size of R0 tells you how bad that epidemic's going to be. For example, I think the common annual flu that we get every year has an R0 of about 1.5. We'll see in a little bit that the R0 for the COVID-19 virus is actually around 2.68. Now, how do we find beta and gamma? In order to solve the differential equations that we showed earlier, we have to know what beta and gamma are. And in the early phases of an epidemic, the number of infecteds will grow exponentially. So if we can get data on how that particular exponential growth is happening, we can determine from that data the values of beta and gamma. So initially, the infective I of t, the number of infecteds, will increase exponentially. During that early phase, the number of susceptibles is approximately constant, equal to the initial value. So from equation B, we would have then this following result that I show right here. You can see that how the di dt equation, we can set s equal to s0. At t equal to 0, I is equal to I0, which is the number of infectives. And we can easily integrate that differential equation to give us the equation shown in the box. Now this equation here would describe how the number of infectives would grow in the early phases of the epidemic, and shows that the growth rate is in fact exponential. And if we know the doubling time, if you're following the number of infectives, you can figure out what the doubling time is, which would be the time it takes for the number of infected to double, as I show down here. Then we can rearrange that result as I show on the next page. You can go through some of the math here. But what happens is you can then solve and find what gamma is in terms of the doubling time for the infection and the reproductive number. So this particular equation, if we know the doubling time and the reproductive number, we can use this equation to solve for gamma, which is one of the parameters in our epidemic model. Gamma in the epidemic model is the rate of removal of the infected population. Now for the COVID-19 virus, there was a paper recently published in the medical journal Lancet that I have the citation for that on the last page of this presentation, and I'll also post the PDF file of that paper on the blog for those that are interested. But they analyzed some of the early data for the COVID-19 infection in China, and their analysis of that data shows that the reproductive number is about 2.68, and the doubling time is about 6.4 days. So using this information, we can calculate the values of gamma and beta, as I show here towards the and the reciprocal of gamma is the actual period of time, on average you could say, that the infection lasts, and we see that it's lasting about 15.5 days. For a U.S. population of 330 million people, that would be our S0 value, we can go back to equation D and we can solve for beta, which gives us a beta value of 5.24 times 10 to the minus 10th per day. Now with these estimates of beta and gamma, we can then solve our set of differential equations, equations A through C. These equations are nonlinear, and we can solve them numerically for the time course of S, I, and R. And we'll look at a Matlab program that easily does that in a few minutes. Now the model solution will look like what I have shown here in this graph. Basically, we've got the number of people. We have the number of people plotted on the ordinate here, and the abscissa we have time. And this dashed line right here would represent the change in the number of susceptibles with time. Kind of follows a curve that looks like that. The solid curve is the infection, the number of people that are infected and how that changes with time. And what's going to happen is as you change the value of R0, if R0 would decrease, we would see that this curve would flatten and broaden, so it would be more like this here. So that's what happens when the R0 changes, and that's what some of the steps that are being taken with social distancing. The whole idea is to try to decrease the R0 for the COVID virus from the current 2.68, try to get that down into the the range of about 1.5 or so that the infection number of infected follows a pattern more similar to maybe a seasonal flu. Now we can solve the set of differential equations using Euler's method. And what we do now is we just lay out the equations like this. We're calling these functions over here, I'm just denoting by f, g, and h. And in Euler's method, what you do is you just write the finite difference form of the time derivative over here, which would be a little change in s, for example. How does s change over a small interval as you go from time I to time I plus 1? And if you would divide that change by a delta t, that would approximate the derivative. And then what we do is we evaluate the functions at the previous time step. So we can use Euler's method basically to predict from a current time what the values of s, I, and r are going to be at the next time increment. So when we do that, we end up with three algebraic equations. We would have a constant time step delta t for the purposes of an epidemic. A time step of a day is probably sufficient, and we would evaluate those functions at say today, and then multiply by 1 day, and we could predict what they're going to be tomorrow. And then we just keep stepping along like that in a sequential fashion, and we can then generate curves that look like that. And all we need to do in order to solve this epidemic model, we just need to know what beta and gamma are and what our starting susceptible population is. Now what I show here is the actual Matlab code that implements the solution of the differential equations using Euler's method. I don't know how well it's going to show up on the video. Let's see if we can take a look at it here. Looks like you might be able to see it, but basically at the beginning of the program we just define what our beta and gamma values are. Then we put in, you can see right here, initial values of the number of susceptibles, infecteds, and removals. So we have that line there. And then we define the time interval. I'm calling that dt, which is, in this case, we're using 1 day. And then we enter in a time for the maximum simulation time. And then we use a simple for loop, which is shown right in here, we use the for loop in order to solve the set of 3 differential equations. And it's very easy to program these into Matlab. You can see I define my functions f, g, and h based on the rate laws that we talked about. And then this set of equations right down here is where we increment using Euler's method the values of s, I, and r. And then we show the output here. You can see I'm using semi-log plots in order to plot the data. So that's the Matlab program, and you can see there's really not much to it to solve this epidemic model. Okay, now that we have the solution to the differential equations that describe the SIR epidemic model, let's do a couple case studies to see what the results look like. Now, for the first case study, I used a number of infected of 1 person. Basically, we're saying that on or about January 1st in the United States, there was 1 person infected. That was about when the COVID-19 started here in the United States. Now, one of the things we don't know is that the number of people actually being tested is very small at this time. So what we'll do is we'll vary this initial number and see what effect that has on the overall simulation. The R0, the reproductive number, is 2.68, and we use the doubling time of 6.4 days, which comes from the Lancet paper I talked about earlier. We showed then that the gamma and the beta values are given here. And one thing I'll point out is that the gamma value is not going to change, or we wouldn't expect it to change with a different R0. This is basically it's the period of time that you have the infection, and whether we have social distancing or not, once you get the virus, we're just saying that you have it for a certain length of time until you become a removal. So in case A then, we'll say then that the number of affected, when you run the model that we just talked about, you will have that the number of infected is about 1,500 by mid-March. That's today, and if you looked at the figures that are being reported, that's about the number of reported cases in the United States right now. So, you know, if we go back in time, and you can see then that this idea that on or about January 1st we had 1 infected person, you can see how rapidly that infection has spread from 1 person, and right now we're still in that exponential phase. What will happen next then, let me just go to the graph and show you what the solution looks like and talk about that. So here's the graph, and let me just zoom out a little bit. So here's our graph. So what we have then is the blue line right here going across. This here represents the change in the susceptibles. And remember, this is a semi-log plot. So this is time down here in days. Time 0 represents early June. We have an R0 of 2.68, and the I0 was 1. And then this is the number of people in millions. So each of these numbers has to be multiplied by 1,000,000. So right here you can see that number is 10 squared. That would be 100 million people. 10 to the 4th would represent 10 billion people. And this point right here then would be the 330 million people. Down here you can see that we have the magenta line, which represents the number of removals, which actually goes to 0 back in January, because that's when it started. And this red line represents the infected. So you can see the infecteds are going to go up, and then it's going to go down as the epidemic progresses. And you can see that number right there, that's 10 to the minus 6 times, has to be multiplied by 1,000,000. So that's our 1 infected person. Now, if we're in mid-March, we're about 75 days out. And if you go up and look at the red line, we're at about a little over 10 to the minus third, and you can see that the model is predicting pretty close to the 1,500 known cases that we have in the United States as of now. We can see on the graph that the peak number of infecteds, if you go up to the peak and you come across over here, the peak number of infected people will be about 90 million people, and that's going to happen about 190 days from the 1st of January, which puts us into late June, early July. Right around then, this model would predict that you'd have about 90 million people infected. Today we have 1,500 people. So you can see why our governors and mayors and everything are rapidly taking steps to try to mitigate this particular epidemic. And then if you follow the infected curves, you can see that it starts to drop off rather quickly. After about 350 days or so, you're down to a number of infected at about 10 to the minus 2 times a million, which would be about 10,000 people. So you can start to see that after about 350 days or so, the infection starts to die out. You can also see that in terms that the number of susceptibles, which is represented by this curve, is no longer changing, and this curve right here is also would be the number of removals is no longer changing. So somewhere out about 300 days out to maybe 400 days, the infection, even in this worst case scenario, would be pretty much over. Now, the number of removals would represent the number of people that actually were exposed or infected with the virus, and you can see that it's about 200 million, which means about 82% of us will have the virus. Now, this doesn't mean that we all get it in the most serious form. Some of us may not even know we had it. Maybe we had some pre-existing immunity that kept the virus at bay. Other people may get the mild cold or flu symptoms. They're saying about 20% of the folks out there will get some serious health effects, may need hospitalization, and maybe on the order of 3% would end up passing away from the infection. Now, it's interesting to take a look at what happens, what's the effect of testing. Let's just suppose that that the people that we know about that have the infection, the 1,500, were actually tested, but we know that there's a problem with testing kits being available. So maybe the actual population of infected is higher than the 1,500 that's being reported here in mid-March. Well, in that case, let's just suppose that the number of infected is actually 10 times higher. So that would mean then in mid-March we should have 15,000 infected. And if that's the case, we can get to 15,000 infected by mid-March by starting with 10 infected people back here in early June. Now, what's interesting is you still end up with pretty much the same peak. You're going to have a peak of about 90 million people being infected, and you're also going to see that the peak is now at 175 days. So the peak really is not that sensitive to the number of people starting out, but it does shift back a little bit the time of the peak. So 175 days, puts us into early June. That, in this worst case scenario, the infection should peak in early June, and it should be pretty much over in about 350 to 400 days. We can see that we're down to 10 to the minus third in terms of the number of infected. If you multiply that by 1 million, that's like having 1,000 people. So from going from 90 million to 1,000 people, that would represent a pretty good change. Still, we're going to have about 300 million people that were infected, and that would give an infection of about 91% of us would actually get the infection. So what we want to do now is take a look at case 2 and see what effect social distancing would have. All these measures that are being taken to sort of separate us, close schools, take universities online, cancel the major sporting events. What kind of effect would all that have? Well, the goal with social distancing is to reduce the reproductive number. So if we could knock that number down from 2.68 to 1.5, what kind of effect would it have on the progress of the infection? So recall that beta is equal to gamma R0 over S0. We don't expect the gamma to change because if you get the infection, you're basically going to have it for the same period of time. And with an R0 1.5 and our initial population of 330 million people, we can see that beta gets reduced now to 2.93 from a little over 5 down to 2.93. Okay, so now we can run the simulation with these new values of beta and R0, which is now we're going to say is 1.5. Our initial population would be, the initial population of infected would be 1,500 because that's how many infected people we have as of mid-March. So the abscissa down here on the graph, 0 would represent mid-March, which is like today or so. And what's going to happen then is the reason we have the 1,500 is because as of today we're introducing social distancing. So that's going to drop the R0 value, and we want to see how the disease progresses from there. So when we do that, we can see that the peak happens at about 360 days. So here's the peak of the number of infected out here at about 360 days, and the number of infected actually drops down to about 20 million people. Also, if you plotted this on a normal plot, it's a little harder to see it on a semi-log plot, but the number of infecteds, that particular curve actually flattens out and broadens. A lot of times you'll hear the experts talking about flattening and broadening the curve, and that's what they're talking about here, and that's what the social distancing is going to do. In fact, it'll kind of spread the infection phase out to maybe a year and a half to 2 years. But the good news is the peak number of infected, if you look at this and compare it to our previous cases with the higher reproductive number, you're actually seeing a reduction of about 80% in the number of infected. So that would be great news. Also, we're going to have about 200 million people that actually get the disease. So we've been able to decrease that through social distancing to about 60%. Now, as mentioned before, there's the problem with testing and so on, and the question of whether the 1,500 cases we have today actually represents the true number. So let's jack that up by a factor of 10. Let's say there's actually 10 times more people that have the infection. So that would raise our I0 as of mid-March to 15,000. And when you do that, you see that the peak infection now happens at about 285 days, which puts us out towards the end of this year. But once again, the peak is still only going to be about 20 million, as we had in the previous case. And that's where the good news lies, because that shows an 80% reduction in the number of people that are infected at any particular time. Also, we still have about 200 million people that would be infected with the virus. So what happens then is basically social distancing is going to flatten the infection curve. It's going to broaden the curve. It's going to slow things down, slow down the progression of the disease. And what that's going to do is allow the medical system to handle and cope with these folks that have the COVID-19 infection, and especially those that are seriously ill. So that's the SIR epidemic model as applied to the COVID-19 outbreak that we're going through right now. So if you have any questions about anything I talked about in this lecture, send me an email or a text, and I'll answer those in the next video when we get started on Monday, March 16th with our online biotransport class. So have a good weekend, and look forward to seeing you on the, I guess, what do you call it, online next week.